Electrophilic aromatic substitution of pyridine. We know that pyridine is an aromatic compound, so like benzene, pyridine can undergo electrophilic aromatic substitution. And the substitution takes place at the third position. The nitrogen is at 1, so this would be the third position. Let's look into the mechanism. This mechanism is pretty much similar to what we have talked earlier in the case of benzene, where in the first step the electrophile will get added to the pyridine ring. So these electrons will go and attack the electrophile, and this is going to give us a carbocation. And since this is the carbon that is losing the electrons now, it should have the positive charge. And in the next reaction, the base will come and obstruct this hydrogen, thrust these electrons onto to form the double bond, so the aromaticity can be restored. And this reaction is fast. Now, why should electrophilic aromatic substitution in pyridine happens at the third position? When you look at the second and the fourth position, you can see that there is an unstable intermediate that is formed. Say, for example, these two nitrogens right here has got an incomplete oct, because of which in the 2 position and as well as in the 4th position, there are only 2 resonance contributors which are relatively stable. But in the 3rd position, we have 3 stable resonance contributors, because of which it happens at the 3rd position. Here is the relative reactivity of benzene, nitrobenzenes and pyridine towards electrophilic aromatic substitution reaction. You can see that benzene is the one which is more reactive compared to the rest of the compounds. Now, why should benzene be more reactive? In order for the electrophilic aromatic substitution reaction to happen, you need the electrons to go and attack the electrophile, right? So that is the first step in the mechanism. In the case of nitrobenzene, we know that the nitro group is an electron withdrawing group. Because it withdraws some of the electrons, not many electrons are available for the electrophilic attack. And in the case of pyridine, the effect of nitrogen is to withdraw the electrons. Here is the electrostatic potential map of benzene and pyridine, and as you can see from here, the nitrogen is withdrawing the electrons through inductive electron withdrawal, and because of which not many electrons are available for the electrophilic attack. And in the case of dinitrobenzene, the electron withdrawal effect is greatly increased, and therefore it's least reactive in an electrophilic aromatic substitution. So in order for pyridine to undergo electrophilic aromatic substitution reactions, the reaction needs vigorous conditions. All of these reactions right here, halogenation, sulfonation and nitration, you can see that a very high temperature is employed. Even with that, the yields of the reactions are pretty low. Say for example here, the halogenation takes place only with 30% yield, and in the case of nitration, it only happens to 22%. So pyridine is less reactive than benzene in an electrophilic aromatic substitution because of the electron withdrawing nitrogen present in the ring structure. Pyridine do not undergo any Friedel-Crafts reaction exactly for the same reasons why deactivated benzene do not undergo Friedel-Crafts reaction. The nitrogen that is present in pyridine is going to deactivate the ring. Therefore, it cannot undergo Friedel-Crafts reaction.